I recreated the picture, but without as much detail here for number 55 on 6-2, so there it is right there. If you read through the problem, basically this is what it says. This is the equation that represents the distance between the dude that's standing here and the boat that's right here in the picture. As you are looking due north, that angle between where the boat would be if it was due north and this guy would be 0 radians. I know it's in radians because they told me somewhere. Oh, right here. So the angle there is in radians, and the line of sight due north is 0. If we go to the left, it's negative, and to the right, it's positive. And the ship right now is to his left, so this would be a negative angle, and it's going to travel in this direction right here. And they actually give us the function for that distance. The first thing they want to know is what is a reasonable domain for that. So basically they're saying, what are possible values we can put in there? How far to the left and how far to the right is he going to be able to see? Well, technically this can keep getting further and further and further, and this can get more and more negative until theoretically it would reach this point right here, which would be negative pi over 2. Sorry, that's not dry. And then once it traveled to the right, the same thing, this would get more and more positive until technically, obviously this is never going to happen, but he's eventually going to be so far over here that this angle is going to be so teeny tiny, but he's going to be way over there, the ship is. So he is approaching pi over 2. Never going to make it there, but he's going to get there. And so the domain is from negative pi over 2 to pi over 2. Then they wanted us to graph this function. So from negative pi over, oh, I have this labeled wrong. From negative pi over 2 to pi over 2. First of all, at negative pi over 2 and pi over 2, that's never going to happen. So those are going to be vertical asymptotes. Also, since we're graphing the secant graph, behind the scenes, we would be graphing the cosine graph. Behind the scenes, from negative pi over 2 to pi over 2, the cosine graph would look like this. Because the cosine graph usually starts up at 1 and then comes on down through. And then, of course, it repeats itself over here. And so instead of going up at 1, though, our amplitude is 1.5, so that's going to be 1.5. And then, of course, our actual graph of this is a parabola between those vertical asymptotes. So that's the graph of that. Find and discuss any meaning of the vertical asymptotes. Well, I kind of already talked about that. The vertical asymptotes are there because although as the ship gets further and further away, this angle right here gets smaller and smaller and smaller. This one's getting bigger and bigger and bigger. This one's getting smaller and smaller and smaller. It's approaching pi over 2, but it's never going to be able to be actually across the river from him. Like it's not going to be able to travel here and be directly at pi over 2. So that's the reasoning behind the vertical asymptotes. Then they wanted us to calculate this. So we're going to put that in the function. Remember, I've said this 100,000 times. This means go find the function. There it is. Replace the input value with negative pi over 3. So that's what I get. So I already have my calculator set up in radians. So I'm going to put 1.5 times, there is no secant button. So what I'm going to put in instead of secant is 1 over the cosine of negative pi over 3. So times, I'm going to put parentheses around this so I don't mess up the calculator. 1 divided by the cosine of negative pi divided by 3. Close off those parentheses. Close off the original parentheses and hit enter, and I get 3. And then I'm going to do the same thing here for pi over 6. So instead of typing all that in, I'm just going to go up there and delete this out and change that 3 to a 6 because I'm too lazy to retype it all. Oops, I didn't need to hit graph. Darn it. Darn it. There we go. And they said to go to the second decimal place, and we get 1.73. So what these represent is these represent a distance at that angle. So when he's traveled when this angle is negative pi over 3, this distance right here is 3, was it kilometers? Yeah, kilometers. And when he travels in this distance for pi over 6, then the distance between him and the ship is 1.73. So that's what those two values are. Then it wants to know when is the minimum, what is the minimum and when does it happen? I think that's what the question was. What is the minimum distance between the fisherman and the boat and when does that happen? So the minimum distance is going to be when the boat is directly above the fisherman. So when the secant, or when the angle here is 0, so we're going to put 0 in there. So when it happens is when, is it theta that they use? No, x. When x equals 0, so when it's directly across from him. So what we're going to do is we're going to find d of 0. So we're going to have 1.5 times the secant of 0. So once again, I'm going to come over here. I'm going to copy that, replace this cosine with 0, 0, 0, 0, and then hit enter, and it's 1.5. So that's 1.5 kilometers away. That's the minimum distance, and it happens at 0. Now for the next one, I did not do a very nice job with this picture. I apologize for that. But we have this rocket, that's my rocket, and it's sitting on a launching pad, and it's 2 miles away from a camera. So this is where my camera is going to be. And the angle of elevation from the ground to the rocket after the rocket takes off is pi over 120x. So this rocket's going to take off, and then the angle of elevation, we'll just pretend that that's in the air. So the bottom of the rocket would be in the air there. This angle that's right here is pi over 120 x. And that's after the rocket takes off and after X seconds has gone by. So they want us to write a function expressing the altitude of the rocket. So they want this height. So we have an angle right here. We have across from that angle, the opposite leg. And we have adjacent to that angle, the adjacent leg. This would be the hypotenuse. So when we have opposite and adjacent, that's going to be the tangent. This comes back from section 5.4 or whatever. The tangent of some angle equals opposite over adjacent. So the tangent of that angle equals opposite, which we don't know, h over x, divided by the adjacent, which is 2. And then they want us to only know what h of x is, that height. So we're going to multiply both sides by 2. And there is our equation. So that's part A. Then they want us to graph that from 0 to 60. So here's 60, here's 0. So when I put in 60 here, that means that at this point I would have 2 times the tangent of pi over 120 times 60. Pi over 120 times 60 is pi over 2. Well, we know what happens at pi over 2 for tangent. There is a vertical asymptote there. And then if this was 0, the tangent, if this was 0, so at this value, when we plugged in 0 there, we would have 2 times the tangent of 0 times that is 0. And the tangent of 0 means go to 0 on the graph, look for the x and y value, which would be 1 comma 0. Take the y value, divide it by the x value, which would be 0. So this all becomes 0. 2 times 0 is 0. So at time 0, this graph is 0. And then remember, the tangent graph goes up to the right, and so that's what it would look like. Evaluate and interpret values for h of 0 and h of 30. So h of 0 we just did. H of 0 is equal to 0, and that means at time 0, because this is time, the height is 0. So we haven't taken off at all. At h of 30, so we're going to now figure out h of 30. So we have 2 tangent pi over 120 times 30, 2 tangent pi over 4, which is 1, so that's 2. So at time 30 seconds, is it? Yeah, 30 seconds. This is the height of the rocket, and that is in miles. So it's 2 miles off the ground. And then finally it says, what happens to the values of h of x as h is approaching 60 seconds, which is where this is happening. What happens there is we have an undefined value. It's getting closer and closer to getting to that point, but basically it's saying that the height of the rocket is getting so far high that we just can't even measure it anymore.